Okay, hi everyone. So in this video, I'm going to be reviewing some important details about accelerated motion that's going to be helpful for the test. What I highly recommend doing is to review your notes, the test review that we had on ClassKick, and basically all the ClassKicks that we covered. But I just want to focus on some important details, just to kind of guide your studying. First I'm going to go over the slides that we had towards the beginning of the unit and kind of highlighting some points from that. Then I'm going to go over some example problems that you're going to want to, really make sure you understand before we get into the test. Okay, so first things first. From the slides, when we talked about accelerated motion, obviously the difference between the first unit and this unit is now we're dealing with changing velocities, right? So that's defined as acceleration. So the definition for average acceleration, that's just the rate at which velocity changes over time. And the units that we're going to use is meters per second squared, right? So it's a meter per second per second. What that says is how much your velocity changes as measured in meters per second, right? So, for example, we also talked about free fall. That's the acceleration due to Earth's gravity. And we know that's about 9.8 meters per second squared going down. What that means is that as you're falling, every second, your velocity changes 9.8 meters per second, right? So if I drop something at t equals 0, my velocity is 0. At t equals 1, after 1 second of falling, the velocity would be 9.8 meters per second going down. After 2 seconds, it would be 19.6, and so on, right? So, hopefully that idea is clear. So there are some examples in the slide. For example, the acceleration of this amusement park ride. Very simple. Change in velocity over time. You just put in the numbers and you're good to go. Now, the dot diagrams. This is something that we obviously we used, but we haven't seen it in a couple weeks, so I just want to make sure your memory is refreshed on how to view these dot diagrams. Basically, the way to think about it is that these dots are representations of the motion of the object. So let me kind of explain. So let's say that you're recording the motion of an object. And to represent that motion, you put a dot of the position of that object at every point in time, right? So you have to be consistent, right? So if you're going to put a dot every second, you have to put a dot for every second for every other position. And by putting these dots down of the position of the object over uniform time steps, you get a sense of how the object's moving, whether or not the object is actually moving, right? So if you have a bunch of dots at the same position, well, the object's not moving during those time steps. And if the dots are equally spaced, then it has a constant velocity. If the dots are the distance between the dots is increasing or decreasing, that there's a acceleration, right? So these 4 scenarios that they present in the slides, we have positive acceleration with positive velocity, right? So we're going to consider going to the right to be positive, going to the left to be negative, all right? So clearly, you see in the first case, let me zoom in a little bit, the spacing between the dots is very small, right? So, it's moving to the right, and it starts off with a low initial velocity. As the car continues to accelerate, the velocity is increasing, and that's represented by the dots being more spaced out, right? So if I put a dot down every single second for this object, it doesn't move very much for the first second, and then it moves some more during the next second, and then it moves even more during t equals 3, and t equals 4, t equals 5. So we clearly see the spacing between the dots is increasing. There's an acceleration, a rightward acceleration if the object's moving to the right. In the second case, the object is still moving to the right, but is decelerating. So that means that the acceleration vector is opposite of the velocity. Basically, it's braking. Okay, so when a car brakes, it's moving with some speed, and that speed decreases as you press on the brakes. Simple enough. And then the last 2 cases, it shows you what it would look like if the car is moving to the left, right? So it's the same thing as moving to the right. It's just now you read it from right to left as opposed to left to right. All right, so now some graphical interpretations. This is very important, is making sure that we remember how to get key information from the graph. So here we have a velocity time graph. And actually, I'll start writing this down in the notes here. So let's just go over all the motion graphs to make sure that we are familiar with the definitions. All right, so let's say I have a position time graph, okay? And I'm going to represent an object that's speeding up. Okay, I would look at all the other examples from previous class kicks, but for now, we're just going to look at an object that is speeding up. So an object that's speeding up on a position time graph, it's going to look like this. Okay, so this is a object that is speeding up. Object speeding up. I'll also add that's from rest. Right, so we have an object, it's speeding up from rest, and the position time graph is going to look like this. It's going to be a parabola. So something to note is that for a position time graph, the slope is rise over run, right? That's delta x over delta t, and that's defined as velocity, right? So we define the velocity as displacement over time. So the slope of a position time graph is velocity. This is for xt graph. If we have a VT graph, there's actually two key pieces of information that you can get from a VT graph. So this graph would look like this on a velocity time graph. It would be a straight line, okay? We see that the slope, the way to think of a curve has a changing slope. So the slope at the beginning is 0, right? So it's, at the vertex of the parabola, the slope is going to be 0. It's going to be horizontal. And then we can see that slope is increasing as this object's speeding up, all right? And if we interpret that as, physically the object's speeding up, well, to speed up means you're going faster and faster, right? The magnitude of your velocity is increasing, and we can see that in the velocity time graph. So for a velocity time graph, slope, again, is rise over run, except it's delta v over delta t, right? So the rise is v, the run is t, and we know that's acceleration. Now the area under a VT graph, that's another piece of information you can get. So the area, you have your delta v times delta t. Now this is by the dimension of the area. Obviously for this graph, the area would be the area of a triangle. Okay, so you have to consider that. We know that area of a triangle is 1/2 base times height. But generally speaking, you have a velocity times time, and we know that's going to be displacement. Okay, so the way you find displacement on a velocity time graph is you look at the area. Another important detail, if the graph is above the horizontal axis, okay, that means you have positive velocity times a positive delta t, right? So you get a positive area. If the VT graph is below the horizontal axis, then you have a negative area. And then finally, I'll just draw it over here. All right, so our acceleration time graph would look like this, right? So we see here the slope. We know slope is acceleration. This velocity time graph has a constant slope, and it's positive, right, because it's going up and to the right. So we just have a constant positive value here, and then we know that the slope of an acceleration time graph, we don't have to worry about that. You can have changing accelerations, but we're not going to really deal with that. What we care about is just that the area is equal to, you have acceleration times time, right? And that's velocity. Or I should say that's your change in velocity. Right, because we know that acceleration is delta v over delta t. Okay, so if you took the area of an acceleration time graph, that's your change in velocity. Alrighty, finally, this part here is going to be important. So we have velocity and acceleration. Here we have if you have positive velocity, positive acceleration, we know you're speeding up and going to the right. Negative velocity, negative acceleration, you're speeding up going to the left. Positive, negative, slowing down to the right. Negative, positive, slowing down, going to the left. And I would check out we had some activities, motion match and motion graphs. So if you really want to, review that to, build up your intuition on motion, right? So how do we represent an object moving? What's its velocity and acceleration? And, what's basically going on in the problem. So make sure you know this as well, right? So having a connection between what the velocity is at some point in time, what the acceleration is, what the object's basically doing. All right, so if you have positive velocity, positive acceleration, the object's speeding up and going to the right. And yeah, that's the first bit that I want to really make sure we know. Now let me go over some examples, right? So some other, actually, let me talk about gravity. Okay, so we did free fall towards the end of the unit, and there's some things about gravitational acceleration that we need to know. So we know that the acceleration due to gravity on Earth, due to gravity on Earth, is 9.8 meters per second squared going down, right, towards the center of the Earth. Okay. Something that's important to note, this is true of all objects. So this is true. So all free-falling objects, accelerate at this rate regardless of the size or mass. So all free-falling objects accelerate at this rate regardless of size and mass. Okay, and we're going to see why when we go over the gravity chapter, right? So when we talk about the force of gravity between objects, you're going to see in the equations that the masses cancel out, right? So that's, just basically how gravity works. It actually doesn't matter what the mass of the object is. The mass, if you have an object with more mass, it will have more weight, right, because it's more massive, but that's canceled out by the fact that the force on it is going to be greater, right? The force acting on the object is equal to its weight. So, we'll be going over those details later, but for now, just accept that the acceleration due to gravity for all objects is going to be the same. Now, we're ignoring air resistance, okay? So we're not going to talk about air resistance right now. We're going to assume for all of these problems that the air resistance is 0. So one counterexample is if there was air resistance, which there is in real life, dropping a hammer and a feather, right? So if you drop a hammer and a feather, obviously the hammer is going to hit the ground first. The only reason that happens, though, is because the air pushes up on the feather, right? So there's this force acting on the feather. We call that air resistance. And basically, it has to push the air out of the way. And due to the size and shape and mass of the feather, it floats down very slowly. But in the absence of air, they would actually hit the ground at the same time. And I'll show you all a video later, which is kind of cool, is there's an astronaut in one of the Apollo missions that they actually repeated this experiment. So they wanted to see, was Galileo right about, all objects falling the same rate? Obviously, we already knew the answer, that it's true. But just for fun, they actually brought a feather and a hammer, and they performed the experiment on the moon, which was kind of cool. But yeah, so going back to what we need to make sure we know, 9.8. Just accept that 9.8 for all of our problems. The way we're going to be working through this, if it's falling under the influence of Earth's gravity, it's no air resistance, is going to fall with an acceleration of 9.8 meters per second squared going down. Always, 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 right? That is how it works. So another fact that's important to note is that the velocity at the peak is 0. All right, and let me draw a picture kind of demonstrating that. So let's say we have some object and we throw it up, okay? And it's going to start off with some initial velocity. So it starts off with some initial velocity. It's going to hit the ground with some final velocity. We know that the velocity at the top, right? The velocity at the very top is 0. And here's the basic argument for that. Well, you can just graph it, and you can see that, if you graphed a position time graph, right, you would see the slope at that point is going to be 0. If you graph the velocity time graph, you're going to see that's when the velocity hits 0, right, when it reaches the peak. But intuitively, think of it like this. If we call up positive and down negative, there's a point where the velocity goes from positive to negative, right? And that's at the very top. And the only number that's between positive and negative, that's 0, right? So when you're going from positive to negative, you have to cross 0. And that's going to be at the very top. Now, something else that's important to note is we just mentioned that the acceleration due to gravity, the acceleration is 9.8 meters per second squared going down. And that is always, always, always true throughout the trajectory of this object. All right, I throw an object up, it's going to be accelerating 9.8 throughout the entire trip. Okay, now let's do some examples. So one example that would be good, I think it's on page 20 from the class kick. All right, so there's a class kick example. There's a class kick example where it's a stopping distance. All right, I believe it's on page 20 for the test review. And let's just go over that example. That's going to be an important one that I want to work out to make sure that we all know how to approach the problem. It's very straightforward. I already know that we got it, but let's just go over it. So we had a car, and it's traveling at 91 kilometers per hour. So we have 91.0 kilometers per hour. And if we convert that to meters per second, you just do dimensional analysis. You know there's 1,000 meters in a kilometer, and there's 3,600 seconds in an hour, right? So if you're going to convert it to meter per second, you're going to end up with 25.3 meters per second. Okay, so that's going to be the velocity of the car. And let's say the acceleration is negative 6.4 meters per second. Meters per second squared, okay? And now we need to figure out the stopping distance. All right, so what's the stopping distance? Well, for this one, let's look at all of our kinematic equations, right? So you're going to have an equation sheet, and I'll have the equations on the board, but let's write them down now, all right, just to make sure we got them. So we know that VF equals V naught plus AT. The second equation is going to be X is equal to 1/2 VF plus V naught times T. Equation 3 is X equals V naught T plus 1/2 AT squared. Right, this X being the displacement, okay? And then equation 4 is VF squared is equal to V naught squared plus 2AX. If you want to give names to these equations, let's name them. Right, so you don't have to think of them as 1, 2, 3, 4. So here we have I'm going to call this one the final velocity equation. This one here, I'm going to call this one the average velocity relation. This one is going to be called the equation of motion. Okay. And then this one is the time-independent relation. So the time-independent relation. Okay. In terms of where these equations come from, well, basically it comes from the definition. So it comes from the definition of velocity, of acceleration, and how they affect the position of the object, how an object displaces, right? So the final velocity equation, this comes from the acceleration equation, right? So delta V over delta T. And we're going to measure an object's motion with initial time equal to 0. You rearrange the equation, you get this equation, VF equals V naught plus AT. The average velocity relation, that comes from the definition of average velocity. So we know that average velocity is displacement over time, right? Delta X over delta T. And we also know that if you have a uniform acceleration, the average velocity, you can just take the simple average. So you do VF plus V naught divided by 2, right? So add them up, divide by 2, that's your average velocity. So keep in mind, you can only do that when the acceleration is uniform, but that's going to be the case for pretty much all the problems we're dealing with. But just keep that in mind. The acceleration has to be uniform, right? The third equation, this just comes from the definitions of what velocity and acceleration are. And then the final equation, if you combine these together, you can end up with the time-independent relation. So using how to know which equation to use in a problem, that's something that's important to know. Well, we've had plenty of practice, and so hopefully everyone kind of has a feel for it. But basically, you just write down what variables you have, what variables do you need, and then you see which equation contains those variables, right? So here, we know we got V naught. So let's go back to the stopping distance problem. This is V naught. This is the acceleration, right? Actually, let's kind of write it out, all right? So I want to be systematic about this. So we know V naught is 25.3 meters per second. We need X. X is our stopping distance. That's unknown. We know the acceleration is negative 6.4 meters per second squared. That's because it's braking. And then finally, there's a piece that's not explicitly stated in the problem, but you have to kind of figure it out from the situation. We know that it's stopping, right? We're calculating how far does it travel in the process of braking. Okay, when you brake your car, when you stomp on the brakes, all right, you're going to end up with no velocity, right? That's what it means to stop moving. Okay, so your final velocity is 0. All right, so we have 3 variables. We need a 4th variable. There's one equation that has all of these variables, and that's equation 4. It has final velocity, initial velocity, acceleration, and displacement. And that's part of the reason why it's called the time-independent relation, is that there's no time. So when you have a problem where there's no time, you don't need time, you're going to use equation 4. So let's just write it out. So VF squared equals V naught squared plus 2AX. Let's just plug in the numbers to make it as straightforward as possible. So we have 0 squared is equal to V naught squared, right? So that's 25.3 meters per second squared plus 2 times negative 6.4 meters per second squared times the displacement x, right? So x's are unknown. If you want to rewrite it using just algebra, right? We know that it's VF squared equals V naught squared plus 2AX. We know this is 0, and then you do the algebra, you find that x is equal to negative V naught squared over 2A, right? Using just the numbers, we have x is equal to, that's going to be negative. So I'm moving this 25.3 squared to the other side. So, because 0 squared is just 0. So we know it's negative 25.3 squared, okay? And then we have this divided by 2 times negative 6.4, okay? And then when you do the math, put in your calculator, you end up with about 50 meters, right? So 3 sig figs, 50 meters. All right, that's the stopping distance. So just one equation, you solve for the unknown. You know, just that's how you approach that kind of problem. And I'm pretty confident we're all going to get this one because it's a straightforward one-step problem. So I was looking at some other problems that would be useful, and I found one from a text, University Physics, and I'll actually post pictures of the kind of full analysis of this style of problem. What I'm going to do for this video, for the sake of time, is I'm going to do a simpler version of the problem. Okay, so I'm going to do a simpler version. This is the melon problem, but I'll post the kind of different versions of the same problem, and they all have the same kind of theme. So that theme is you have 2 objects that are falling, basically, in free fall, and those objects are going to meet. So in this case, we have a melon. So someone drops a melon. All right, so we have a dropped melon. Okay, so this melon's going to fall down some distance. And then here we have an arrow. All right, so here we have an arrow. Someone shoots up an arrow, and they're going to meet at some point. Right, so this object's, they're going to meet at some point. All right, so we have a dropped melon, and then we have an arrow shot from bow. Okay, and there's many different things that you can ask with this type of problem. You can figure out, you know, if the arrow has this velocity, at what point does it actually hit the melon? At what time does it hit the melon? Or if they tell you at what position the melon and arrow hits, can you figure out the velocity of the melon? Or not the velocity of the melon, I'm sorry. Well, I guess both. The velocity of the melon and arrow when they hit each other, the initial velocity of the arrow. There's all these different ways to ask about this kind of problem. And again, I'll post the pictures from the text just so you can kind of see how they work it out. I'm going to do a simple version of this problem where, let's say, the melon and the arrow, they meet at the same point. Okay, so let's add some numbers to this. All right, so let's say that the melon is 60 meters above the student's head. So let's say the melon is 60 meters above the archer. Okay, so there's a guy sitting down here with a bow and arrow, and he's going to hit this melon with his arrow. And then hopefully he gets out of the way. So now we know that the arrow, so arrow is shot at the same exact time that the melon is dropped. Okay? So let's say that the melon and arrow meet halfway. Okay? So if this melon is 60 meters above the arrow, well, halfway, that's going to be 30 meters. Okay? So that's going to be 30 meters up from the arrow and 30 meters down from the melon. Okay? And let's say we need to solve for the velocity of the arrow. So what was the initial velocity of the arrow? All right, so basically in this problem, you're looking at the motion of two different objects. You're relating them through one of the variables, and then you're solving for the unknown. That unknown being the initial velocity of the arrow, right? So V naught of the arrow, that's unknown, and we got to figure it out. All right, so let's write out the equations. One equation I want to give you, in addition to the 4 kinematic equations, I want to let you know about free fall. Okay, so free fall, let's say you drop an object, or I'll call this a free fall equation. All right, so it's a useful shortcut, and I'll show you where it comes from. So if you drop an object at some height, and it falls some distance y, and you're going to be measuring how long it takes to fall this distance y, okay, there's an equation for that. So the way you figure this out, we know that the acceleration is 9.8 meters per second squared going down. And if I were to write this out, let's say this is the displacement y, so the height at which the object falls, right? So how high up is the object from the ground, and how long does it take to actually fall? Okay, so instead of x equals v naught t plus 1/2 at squared, I'm going to use y. So y is equal to v naught yt plus 1/2 gt squared. Okay, so this g being negative 9.8. Okay, so negative 9.8. Right, calling out positive. I think in the book, they say that they give the value g 9.8, and then in the equation they put minus 1/2 gt squared. But just understand that that's essentially the same difference, right? Just keep in mind what you're calling positive, keep in mind what you're calling negative, and the math's going to be working out all the same. So the way we get the free fall equation, we know that this is 0, and if we want to solve for t, right? So it's typically, that's like the reaction time problem. When we had the experiment in class where we were dropping the ruler and we catch it, that problem's also going to be posted as a picture, right? That's also in the text. It's a classic problem, so definitely review it. But, we're figuring out, based on how far the meter stick fell, we calculated what our reaction time was. Same kind of setup. So we have here y equals 1/2 gt squared. Okay, and then if you solve for t, you know that t is going to equal the square root of 2y over g. Okay, and that's the free fall equation. I'll write that up on the board so you have it as a shortcut. This works when the initial velocity is 0. Okay, so the initial velocity is 0, you drop an object, you want to figure out how long it takes to fall some distance. You can just go straight into that equation. All right. So it's a useful shortcut, or you can just figure it out from equation 3, right? It's not that difficult. We're going to use that shortcut for this problem. All right. So, again, you can figure, I think in the book, the way they set up the melon problem with how they do it, they just use equation 3 for both cases. All right. But for the sake of keeping it simple in terms of how to approach this one, we're going to use the actual free fall equation. So the relationship between these two scenarios, all right, so we know that for the melon, it's going to fall some distance y, right? So we'll use y. And it's the same thing as using x, all right? We're just going to call it y because it's in the vertical direction. So the distance that the melon falls, okay, that's going to equal v naught yt plus 1/2 at squared. right? A being the acceleration due to gravity. But you can just use a shortcut, right? So we know that the initial velocity of the melon is 0, right? So if that's 0, basically it's just a free fall problem, okay? So the time that it takes the melon to fall is going to equal the square root of 2y over g. And that's basically how you want to approach this problem, because we know that the melon's going to hit the arrow at exactly halfway up, but also we know that they're shot at the same time, right? So they're shot at the same time, okay? So they're shot at the same time and they hit each other. Well, the duration of time for the motion of the melon and the motion of the arrow should be exactly the same, right? They were coordinated. So I dropped the melon and I shot the arrow at the same time. So they're going to hit each other at the same amount of time, right? However long it takes for the melon to fall and the arrow to rise, it's the same time period, okay? So to solve for the arrow, right, we're trying to figure out the initial velocity of the arrow, right? Well, in order to do that, let's write out the equation for the arrow. So the arrow is going to go up some height, okay, that is going to displace 30 meters. We have v naught, this is for the arrow, t plus 1/2 at squared. All right, we know the acceleration is going to be 9.8 going down, and we're trying to solve for that v naught. All right, but we know that the t for the melon is equal to the t of the arrow. Okay, so we can figure out the t of the melon, and then we can figure out what the velocity of the arrow is going to be. So let's actually just solve it out. So we know the t of the melon is going to be the square root of 2 times 30 meters divided by 9.8 meters per second squared. All right, and then we calculate it. You have square root of 60 over 9.8, and you should end up with about 2.47 seconds. All right, so that's the first part of the problem, is figuring out, how long is the melon falling for, right? So we know it's going to fall 30 meters. How long does it take for the melon to fall 30 meters? And we know that at, 30 meters of height, that's when the arrow hits the melon, right? Because we just said they hit halfway, and the melon was 60 meters above the archer initially. So we know the time. We can plug that in for the time of the arrow, right? So this is for the arrow. This is for the arrow. And again, this is the height of the arrow when it hits the melon. And we're trying to solve for the initial velocity of the arrow. So let's just start plugging some numbers in. We know that the arrow is going to move upwards 30 meters. And that equals the initial velocity of the arrow times the amount of time it takes, so 2.47 seconds, for the arrow to hit the melon, right? So after 2.47 seconds of motion, that's when the two objects hit each other, plus 1/2 at squared. Now with this, if we're going to call the height of the melon, the height of the arrow, so the arrow is going up 30 meters, right? The arrow moves up 30 meters. I don't know why it's doing that. So it goes up 30 meters. All right, well, gravity goes down. And the acceleration rate of gravity is 9.8 meters per second squared. So if we're going to call 30 meters positive, right, and in this case, gravity is going to be negative 9.8. All right, and I want to get everyone used to the idea of kind of playing around with the direction that you call positive. Is up positive, is down positive. It all just depends on how you want to set up the problem, right? And either way, you're going to get the same answer. But generally speaking, if you call the, whatever you call positive, whatever you call negative, it doesn't make a difference. You're going to still end up with the same answer. See, in this case, when I was talking about the melon, I said the melon falls down 30 meters, right? And I would consider down to be positive. I could just as easily say it's negative 30 meters, and I could just as easily put negative 9.8. The negatives cancel out, all right? But yeah, in this case, we're calling up positive, so that's going to be negative 9.8. And then the time is 2.47 seconds squared, all right? And let's solve it, right? So you can just use pure algebra when doing this problem, but I found that it's less likely for students to mess up if they just start working with the numbers. I mean, you have a calculator, right? Use it, right? It's a helpful tool. So we can just start plugging in the numbers and we can calculate it. and I get approximately -30 for this part. All right, so I have 30 meters here, and I have 2.47 times V naught, and then it's plus, it comes out to approximately -30. Okay, so it's about -30. And then here, I have to move that -30 to both sides, to the other side of the equation, right? So I'm just going to add 30 to both sides, and I end up with 60 is equal to 2.47 times V naught, okay? And then V naught is equal to 60 divided by 2.47, okay? This is for the arrow. You plug that into your calculator, and you should end up with, what do we get? 24.3. All right, so for this problem, again, let's recap. What did we do? So we dropped the melon and we shot an arrow up at the exact same time, and they hit each other halfway up. Okay, so the melon is 60 meters above the arrow. They hit each other halfway, which is at 30 meters. So the arrow went up 30 meters. The melon fell down 30 meters. For the melon, because the initial velocity is 0, it's just a free fall problem. Okay, or you can use the free fall equation, right? So it's a free fall problem where you can just straight up use the free fall equation. So you want to use it to keep it simple. We solve for the time. We know that the melon takes 2.4 seconds to fall, right? For it to fall 30 meters, that takes 2.47 seconds. We know that's how long the arrow has been traveling, because they have to hit each other at the same time. And then we plug it in to the equation for the arrow, and that's how we solve for the velocity of the arrow. All right, so this is like a two-step kinematic problem. Yeah, I just want to make sure that we see how to do this. One more example I'll give, and this will be the last one. It's how to think about a kinematic problem without using any numbers. Okay, so this is something that we have not done very much of. You can kind of do it when you're looking at, say, deriving the free fall equation, right? When we derive the free fall equation, I didn't even have to use 9.8, right? I just know it's square root of 2I over g. G could be different for different planets, right? If you're on the moon, the acceleration on the moon is going to be different than on Earth. I can still use the same equation. Instead of using 9.8, I use whatever the acceleration on the moon is. I think it's about 1.8. It's quite a bit smaller than the Earth's, right? So that was just using pure algebra. I didn't use any numbers. So I want to do another problem that uses pure algebra, so you can kind of see how to approach it. So basically what this problem is how can we show, let's look at the lab that we had where we were calculating the hang time, right? So say you jump up and you reach the peak. Okay, so this is T peak, right? And we also measured the hang time, right? So the hang time is going to be the amount of time it takes to jump up to this max height, and then you have the amount of time it takes for the object to fall, and then the hang time was T peak plus T fall. Now in the lab, it explains that the amount of time it takes to jump up, right? We calculated that by placing the tape, right? So we placed the tape, we reached our hand up, placed the tape as high as we could, and then we did the same thing with another piece of tape by jumping up. We measured the distance, we know how much we jumped, we put in the free fall equation, and we calculated how much time it took us to jump, right, from the free fall equation. From that, we said that, all right, well, the amount of time it takes to fall down should be the same. And so you can just multiply by 2, and that gives you your hang time. All right. Now let's actually prove that. Let's show that the hang time, right, so the T peak, the amount of time it takes you to jump up, is equal to the amount of time it takes you to fall back down, right? So intuitively, we know this just due to the symmetry of the problem, but let's show it mathematically by using the kinematic relations. So with this, we have here, how we would want to approach this problem. So let's think of it as, say, we're going to jump up with some initial velocity. Okay, we're going to reach the peak. And this is we're going to be looking at the time for the peak. Okay. Now, one way you want to express this is, as I stated earlier, right? So one thing that we know is that the velocity at the very top has to be 0, right? Because basically you're moving up with some positive velocity, and then you're going to be coming down with some negative velocity. So by definition, the velocity at the very top has to be 0, right? So that's something you need to know. So at the peak, the highest that you can jump, right? So at the peak, the velocity is 0, right? So I'm going to call that VF. We know that VF is equal to 0. So let's set up the equation. So we know the acceleration is 9.8 meters per second squared going down. I'm going to call that negative, right? So we're going to call down negative, up is positive, and down is going to be negative. All right, going down is going to be negative. Okay, so in this case, our acceleration is negative 9.8. All right, but we're not even going to be using numbers. We can just use g. All right, so we know that's going to be g, is 9.8 meters per second squared going down. So here we have VF is equal to V naught plus AT. That's the final velocity equation. All right. And so the way we're going to represent this is we need to solve for the peak time, right? So this is going to be T peak. And we know the final velocity is 0. All right. So the final velocity is going to be 0. So the T peak is going to equal negative V naught. So I have a positive velocity, right? And all I did was I moved the V naught to the other side, okay? So it's going to be negative V naught divided by A, right? In this case, A is negative 9.8. So I have a positive initial velocity. We see there's a minus sign in front, so I get a negative number. The acceleration is negative 9.8. We're not even going to write that down. We're just going to express it mathematically. And we just put an A down there. We know it's going to be a negative number. All right, so that's our peak time. Okay, now let's look at our fall time. All right, so say we have now the second part of the motion where the object's falling. Well, when the object's falling, okay, we know that it's going to have some final velocity going down. And we know that the initial velocity when you're falling is going to be 0, right? Because you're at the peak and now you're going to start falling down. So basically we're looking at the second half of the motion. All right, let's write out the equation for that. So again, we have VF is equal to V naught plus AT. This is A, it's lagging a bit now. So this is A times T of fall. Okay. Now in this case, V naught is 0 because we're looking at the second half, right? So at the very top, your velocity is 0. And we have an expression where T fall is equal to VF divided by A. All right, so I have these two expressions, VF divided by A for T fall, negative V naught divided by A for T peak. And the important thing to identify, right, in order to show that these things have to be equal, because I have V naught and I have VF, right? So basically, when you accelerate, we have a uniform acceleration. We know that the velocity equals 0 at the peak. Okay, so what that means is that the velocity going up has to equal the velocity going down, right? If we reach the same position, that position being the floor. Okay, so I start off, I jump off the floor, I'm moving up with some initial velocity, I'm uniformly accelerating, right? And then I reach the peak, and then I come back down under that uniform acceleration. I know that my initial velocity has to equal the negative of my final velocity, right? So I'm calling up positive, I'm calling down negative, and that's basically how you approach this kind of problem, right? So the fact that the initial velocity has to equal the final velocity, they're just in different directions, okay? You can even graph it to kind of show with the graph, right? So I start off with some initial velocity, right? So this is a VT diagram. I start off with some initial velocity. I end up at some final velocity, all right? And we know that it's going to be 0 at the very peak, right? And over here, I reach this final velocity. I mean, you can also show this by just understanding that the amount of height that you jump up is going to equal the amount of height that you jump down. So you don't even have to prove it this way. You can prove it by using the free fall equation, right? So it's square root of 2y over g. You have the same y in both cases. The height that you jump is going to equal the height that you fall, right? The floor didn't move. Okay, so you can even use this equation to show that they have to equal each other. But I'm doing it now using the velocity equation. Either way, you just have to work through the equations to show that they basically equal each other. So Vf is equal to negative V naught. I can rewrite T fall. So, oops, let me keep this in white. So I can write T fall has to equal negative V naught divided by A, right? Because, you know, V naught is equal to negative Vf. That's the same thing as saying Vf is equal to negative V naught, right? And so having this understanding here, right, that, you know, Vf equals negative V naught, that shows you that the fall has to be the same, right? So I'm writing two different expressions, but we see the equal the same thing, right? So the amount of time it takes to fall is negative V naught over A, and the peak time is going to be also negative V naught over A. Another thing you can show is the hang time. So why is the hang time equal to 2 times the peak time? Right, because that's what we did in the lab. We just said the hang time is equal to 2 times the peak time. Again, there's many ways to show this. One way to show that is by using equation 3, right? So if I jump up and fall back down, okay, my displacement is 0. Right, so let's just use equation 3 to show this. So you have x equals v naught t plus 1/2 at squared. Let's see here. Okay, so yeah, let's do that. So we have x is equal to... Actually, let's use for this one, because I don't necessarily want to put it in terms of v naught. No, we can. That's fine, because it's going to work out all the same. So we say the displacement 0. This is for the hang time, the amount of time that you're actually in the air. Okay, so we don't know what V naught is. We're going to leave this all in algebra. We're not using any numbers, right? So that's kind of the whole point of this approach to the problem, is you're seeing how do the equations connect to each other, right? When you're looking at a certain scenario, right? And how can you come up with these other relations, right? The fact that the fall time equals the peak time, the fact that your hang time is twice the peak time, and, you know, how do we know this mathematically? And that's basically what we're going over now. So let's just write that the displacement 0, because we know that the hang time is going to be... for the hang time, you jump up, you come back down, you have no displacement. So I'm going to put a 0 in for the displacement. I'm going to still leave this V naught t. I'm going to call this hang time, so t hang, plus 1/2. I forgot to put a squared there. So 1/2 a times t hang, right, hang time squared, okay? So now let's solve for this. In order to solve for t, what I can do is I can divide both sides by t. Right, so I can divide this by t hang, and I can divide this side of the equation by t hang. Okay, and what I end up with is 0 is equal to v naught plus 1/2 a times t hang. Right, because this is v naught t divided by t. Well, it's just v naught. 1/2 at squared divided by t, that's 1/2 at. Now let's solve for t hang. So I'm going to subtract both sides by v naught. I get negative v naught is equal to 1/2 a t hang. All right, multiply both sides by 2, and then divide by a. I get t hang is equal to negative 2 times v naught over a. Oh, and guess what? T fall is negative v naught over a. T peak is negative v naught over a. T hang is negative 2 v naught over a. So without using any numbers, just showing the kinematic equations, we know that the hang time, so we know that T fall equals T hang. Oh, whoops, not T hang. T fall is equal to T peak, okay? And we know that, the the hang time, is how long it takes you to jump up to your max height, how long it takes you to fall back down. All right, and these two are equal to each other, so you can just say that T hang is equal to 2 times T peak. And again, the whole point of this problem, when we did the lab, we just took that for granted, right? And it's like, yeah, well, T hang has to equal twice the peak time. And it made sense just based on the symmetry of the problem. But, you know, we need to understand where that comes from mathematically. If you analyze the situation, right, we see that the hang time has to equal the twice the peak time, and that the peak time equals the fall time, right? And we showed this mathematically. I came up with an expression for the peak time. I showed that the fall time has to be the same. It equals the same expression. And I just showed that the hang time is twice that expression, right? You see there's a 2 in front of the V naught, all right? And even though we know this intuitively, there's a difference between just knowing something intuitively and being able to show it from the kinematic relations. We have these kinematic relations that are built up from the definitions of displacement, velocity, acceleration. And based on these definitions, you're able to show all these different relationships. And this all works out due to the fact that the acceleration due to gravity, free fall, that acceleration is constant, 9.8 meters per second going down. But we didn't even have to put 9.8 in. We can use any number, right? It could be on Earth. It could be on the moon. It's going to be the same scenario. So I hope this kind of made sense, right? How to just use the equations to show these other relationships. To review some more, we saw the melon problem. So this is a simplified version of the melon problem and how to approach it. And you approach these kind of problems all the same way. It's ones where you have two different objects moving, right? So you have two different objects moving. There's a relationship between the two objects. We've done plenty of these. There's the one with the cop car catching the, what's it called? The Explorer, right? There was one about like the tortoise and the hare. There's equation systems and problems where there's two objects. There's two objects and they're related in some way, and you use that relationship to solve for the unknown, right? So a slightly more complicated kinematic problem. The melon and the arrow is a classic one. And then stopping distance, this one we should all be getting 100%. I have no doubts, because this is just a one-step problem, right? And then you can turn it into a two-step problem. I think there was one we had with the two cars that are going towards each other, right? So two cars are going towards each other. What's the minimum distance between the cars? Review that problem as well. And it's the kind of the same idea. But you know, if you have any questions, if you want me to follow up with any other problems, going over whichever problems from the class kicks, just let me know. But definitely review your class kicks. If you've done the what's it called? If you did the class kick for the test review and the problems were making sense and you're getting the right answers, then you're in good shape, right? You should feel confident going into this test. If you're able to follow along with these examples and more of the examples I'm going to post, then you're going to be in good shape. Yeah, that's pretty much it. I would recommend not only just watching this video, which we'll see how long it is, but I would also study for an hour, right? So just reviewing problems, doing some more practice problems, going through your notes, like spend at least 1 hour, preferably 2 if you can, because again, I want us to do very well on this test. And all it is just practice, right? That's the only way that's how you get good at anything, is you just have to practice. Okay. So, again, if you have any questions, just send me an email. And good luck for the test.